Hi, my name is Pramod Rao, and my project is a novel deep learning approach for low-cost mobile diagnosis of diabetic retinopathy. The purpose of this project was to create a low-cost standalone mobile device with the ability to automatically detect the severity and presence of diabetic retinopathy in patients in real time. Some background on diabetic retinopathy. Diabetic retinopathy, or DR for short, is a disease of the eye caused by diabetes and often leads to the loss of vision and usually shows no symptoms in its earliest stages. It's most often diagnosed through a retinal fundus exam in which a doctor views the retina or fundus of a patient using a fundus camera. These cameras are expensive and can cost thousands of dollars, and additionally, these exams also require dilation drops in order to enlarge the pupils, and some patients may be allergic to these drops. And in addition to this, the cameras are also not portable. So early detection of DR is vital for preventing or delaying the onset of blindness. So here we see a healthy fundus versus a fundus with moderate DR versus a fundus with proliferative DR. The difference between the healthy fundus and the fundus with proliferative DR is rather pronounced due to the hemorrhages, because they're these little green circles in the rightmost image. But it's worth noting that that's a very extreme case of diabetic retinopathy, and it's generally not clear. It's generally more like the fundus with a moderate DR, and the average person with no clinical training can't really see the difference between the two images. And that's why to diagnose DR, you generally need an ophthalmologist's help. Some background on deep learning. Deep learning works by attempting to mimic the structure of the brain through the use of artificial neural networks. Convolutional neural networks provide for an effective method of image classification, and generative adversarial networks are a more recent type of neural network for the generation of new data from a training set. So here we have a diagram of a neural network, and so neural networks consist of layers. The first layer on the left is the input layer, and the input layer in this case would be the image, the fundus image. And then the hidden layers essentially process this image, and then the output layer classifies the image in classification problems. So some engineering goals for this project. The first one was to create a classifier with an accuracy of at least 75% in classifying images. The second was the fundus should be under $100, and the fundus should be non-mydriatic, and that means not requiring eye drops. So the first thing that needed to be done was data augmentation. And so in deep learning projects, it's important for data to be balanced, because this allows for higher detection rates and higher accuracy rates. And rather than using traditional techniques for data augmentation through transformations such as basic rotations and reflections, a generative adversarial network was created and used for image augmentation in this project. And so GANs actually possess multiple major advantages over standard image augmentation techniques, as they produce completely new and unique data. And not only is this useful to aid in diversifying a training data set, but also in the event that one is dealing with private or identified data, as generating a new data set can alleviate privacy concerns. And I should mention now that all programming in this project was done using a Python, and all of the models were trained using an RTX 2060 graphics card, and it was done in a Jupyter notebook called Colab. So as we can see here, the distribution of the data in our training set was rather skewed over into the category of no diabetic retinopathy, which is why data augmentation is important, so that we don't have a falsely high accuracy rate. So FundusGAN, which was the name of the GAN created to generate these images, it output a 448 by 224 image, which was then split into two 224 by 224 images. And 10,000 additional images were generated for each class using FundusGAN. And these additional images help create a more robust diabetic retinopathy classifier. And so here we can see the generation for the first 50 epochs of FundusGAN. And so we can see the model got better at creating these fundus images. And all of the training data was grayscaled and then downsized to 224 by 224. So the image classifier, again, the criteria was to have a 75% accuracy in classifying images and use a convolutional neural network architecture. So the process was to use 35,000 de-identified and anonymous images of varying quality taken from Kaggle.com along with images created by the GAN. Then these images were then turned into an array so that they could be processed by the neural network, and then a convolutional neural network was then built using the TensorFlow machine learning library. And a classifier was then trained and tested. Using the array, where 80% of the data was used for training and 20% for validation. And now we move on to the fundus camera. Again, I wanted it to be inexpensive, use a Raspberry Pi computer, and be non-mydriatic. And the materials are shown here. And so to create the fundus camera, the process is shown here. And then here we can see the fundus camera. So we have the touchscreen display, and then you can see the Raspberry Pi computer and camera. And then this was the PVC used in the lens as well. And so the inside of this PVC was actually painted black. And so I was able to get these condensing lenses by contacting a company and asking for samples. So in conclusion, a convolutional neural network was created. A classifier was also created with an accuracy of 78.39%. Additional training was generated through novel use of a generative adversarial network named FundusGAN, and the fundus camera was built using the Raspberry Pi computer, showing proof of concept. Unfortunately, the camera was never formally tested on humans due to the COVID-19 pandemic. Additionally, the camera costed $85, meeting the criteria of being under $100. And some future plans that I have and would like to try are to increase the accuracy of the model, try other neural network architectures, and see if that would improve the accuracy, and observing how other optimizers affect the accuracy of the model. I would also love to test at some point the effectiveness of the fundus camera on real patients with diabetic retinopathy. Here's my bibliography. Thank you.